This is just a quick reminder that you should feel free to pause the video if you ever feel you want more time to think and write. Welcome everybody to Chapter 5. I am your host, Mr. Bergman. If there's anything I can do to make your stay here in Chapter 5 a pleasant one, please do not hesitate to ask. We are going to start off with inverse functions. This is our first day of inverse functions, section 5.11. Here's the big question. What happens when you switch the input and the output of a function? We've been dealing with functions for so long. What just happens if you just switch them? Literally, like, take the input is 2 and the output is 4 and just switch them around. So you get 4, 2. Or so you get 3, negative 1. Or so you get 0, 2. The input and the output have literally just been switched. What we're going to do is we're going to call that an inverse relation. And if you interchange the first and second coordinates of each ordered pair in a relation, it produces the inverse of that relation. So here's the relation, and then here's the original relation in blue, and then the inverse relation is in red. Now if you graph these, you'll notice something funny happens. All the originals start here, they're graphed, and then they get reflected over a line. The reflections that we've seen so far have usually been across the y-axis or the x-axis, but when we switch the input and the output, when we switch the x value and the y value, we reflect it over the line y equals x. It goes, the x value turns into a y value, and the y value turns into an x value. And they get flipped over this way, reflected over the line y equals x. If you were to do that with the variables, what that would look like here would be the interchange of variables in the relation y equals x squared minus 5x. And the inverse would therefore be, you write the exact same thing again, except every time you see a y, you write an x. And every time you see an x, you write a y. So there's the inverse relation. And that's what it looks like in equation form. This is point form. This is equation form. And so you can define what an inverse relation looks like as an equation. If a relation is defined by an equation, interchanging the variables produces the equation of the inverse relation. So here we're just dealing with the variables. And you can see here the original is a parabola, y equals x squared minus 5x. And then when you flip that over the line y equals x, you get the inverse relation. X equals y squared minus 5y. Pretty fun stuff. Now, how could you graph that, or how could you figure it out even if you weren't flipping it over the line y equals x? Well, what you could do is you could just write a table, equation table graph. And what we used to do was we used to write this down and choose x values and then have it produce the y values. Well, actually, because it's written this way, it might be easier to just choose the y values and then have them produce the x values. So you take negative 1 and you put it in here for y, and you put it in here for y, and you calculate and you get positive 6. Same thing for 0, that's 0, 2 produces negative 6, 4 produces negative 4. You can plot those points and then connect the dots. So the next question is going to be, is what you produce when you make an inverse, is it going to be a relation? And just to remind you, here are some examples of, the big question is the inverse that you produce, is that going to be a function? Here's what a function is, to remind you. Let's say the input was the year, and then the output were the just how much a stamp costs, a first-class postage stamp in cents. So back in 96, it was 32 cents. In 98, it was still 32 cents. Then they hiked it up a little bit, and for 2002 it was 37. For 2009, it was 44. This is definitely a function because every input has an output. I could give you the year, and you know exactly how much a postage stamp costs. So if I say 2004, there's only one answer. It's 37 cents. Same thing here. If you take these numbers and you cube them, then yes, this is going to be a function. It only has one particular output. I'll give you any number, and it only has one cube. Negative 3 goes to negative 27. Now, if we were to take the inverse of these, like flip them around, is the inverse relation of function. And you can see here that although you could say 42 cents, there's only one answer, 2008. You could say 39 cents, there's only one answer here. But if you try and say something like 37 cents, then you don't, as an input, you don't know what the output is. It could be 2002 or 2004. Same thing here. So for this reason, this particular inverse relation is not a function, even though this one is. You can take the cube root of any of these numbers and get exactly one number out. So the big question becomes, is the inverse of a function also a function? And if it is, then we're going to call that original function a one-to-one function. And you can think of a one-to-one function as a function whose inverse is also a function. That's not actually the core definition, it's a result of the core definition, but we're just going to say if it's a one-to-one function, it's a function that also has whose inverse is also a function. Take this function here. If you look at this function, you might notice that helium is the second element of the periodic table. We're going to go elements of the periodic table, and the audio check is helium. So here you can see this is a function. Yes, every input has exactly one output. You can put the input here and get one output. Fine. But if you notice, every output, every y value has exactly one input. It's one-to-one. If you were to take its inverse, let's see if I can flip this. If we were going to take the inverse, that means we're going to reflect it over the line y equals x. Then it would go like this. It would be this line, which is also a function. Here, the line y equals, or f of x equals x squared. The original, as plotted, is definitely a function. You take negative 2 and it goes to 4. You take positive 2 and it goes to 4. Every input has exactly one output. But as soon as you take the inverse, you notice that 4 as an input has negative 2 and positive 2 as an output. So therefore the inverse is not a function. And how did I spot that? Well, one way that I could do it, and you're going to formalize this in a second, is I drew a horizontal line. And as soon as I drew a horizontal line, I could see that there are these 2 points right here that are intersected by that horizontal line, 4. So if negative 2 and positive 2 have an input, if those are the input values, then 4 is the output value. You can see that this horizontal line connects 2 points that illustrate that it is not a function. These horizontal lines are going to start showing up more and more, and in fact we're going to have what's called a horizontal line test. Very much like the vertical line test. Here, we can see this particular graph is, when you draw a horizontal line, it'll only intersect one point, not like the previous example over here. This, we've got only 1 point, and it doesn't matter what horizontal line you draw at any height, these horizontal lines are only going to pass through once. So therefore, yes, you can say you're not going to have the same problem you had before. This is going to be, the question, is this one-to-one? Yes, it's 1 to 1, meaning its inverse is also a function. This is a function, and its inverse is also a function. Check this out. Here's the original function. It's pretty funky. It goes like this, and you can see if you draw a horizontal line at y equals 35, then it illustrates the fact that these 3 x values all have the same output value. Negative 2.5 goes to 35, negative 1.5 goes to 35, 2.5 goes to 35. So the original is definitely a function. It passes the vertical line test. But now we wonder if it passes the horizontal line test. The horizontal line test. Because as soon as you take the inverse, all of this gets flipped. All of a sudden we have 35 as an input, and it could have 3 different outputs. So I want you to tell me, is this a function? Is the inverse of what is graphed, is that going to be a function? So just comparing, we're going to formalize this into a test, the horizontal line test. And you might remember what the vertical line test is. It tests if a relation is a function. And you can see you draw a vertical line, and yep, since it only intersects at one point for each vertical line, then it is a function. The horizontal line test is going to test to see if the inverse is a function. It went from vertical to horizontal because it got flipped over the line y equals x. Anyway, this fails the horizontal line test, so therefore the inverse is not a function. This fails the horizontal line test. We draw a horizontal line, and if it's possible for a horizontal line to intersect the graph of a function more than once, then the function is not one-to-one, and its inverse is not a function. So that's the horizontal line test. It doesn't test to see if the relation is a function. It tests to see if the inverse relation is a function. Here. So we wanted to say that before what I said was that when I said that the one-to-one function is here a function whose inverse is also a function, it's not the actual definition, but a result of the actual definition. The actual definition looks like this. The actual definition says if a function is one-to-one, one-to-one if for different inputs have different outputs. That is, if you have two different input values, a and b, and they're not the same, then you put them into the function and you get values out, and those values should also not be the same. Here you could also flip that around and say f as a function is one-to-one if when the outputs are the same, then that implies that a has got to equal b. If these two different outputs are the same, then you know for a fact that these inputs are also the same. Here's another result of the definition. So if one-to-one, if this function is one-to-one, then it can also be either always increasing or always decreasing. We see that in the original graphs here. This is always decreasing, so therefore, yes, it is one-to-one. This is always increasing, so therefore, it is also one-to-one. For our purposes, you can say that. Here, this is decreasing and then increasing, so we can see it's not going to be one-to-one. Here, if we want to prove that 4 minus x is one-to-one, we can start with a definition. If you want to prove something, and you're going to have to, this is just a really quick proof. It's not like a full-on geometric, two-step column proof, but we want to make sure that we know how to prove something. So here we're going to try and prove that this function is one-to-one. So you start off with either one of the ifs or the, in this case I think it's easier to start off with f of a is equal to f of b. And if you knew that f of a were to equal to f of b, you could just take a and plug it in here to the function. 4 minus a is equal to 4 minus b. So if this function actually is one-to-one, then you can say that this is true. And so then you subtract 4 from both sides, and you multiply both sides by -1, and you can actually get a equals b, and there it is. You can't always do that with all functions, but if the function is one-to-one, then you can say that this is true. We're connecting the blue statement to the yellow statement, blue statement to yellow statement. Now, if we want to prove that x squared is not one-to-one, you can start with a counterexample. So if we're going to assume that f is one-to-one, and then so we're going to say, for example, here, we're going to assume it's one-to-one, and then start with this. Start with two values that are not equal to each other. So we know that -2 is not equal to 2, for example. But I chose these two numbers because I know it's going to help me with my counterexample. If it's one-to-one, then we should be able to say that this a value that is not equal to this b value will also imply that f of a should not equal f of b. Now, if we actually plug them into the function, we get -2 squared. It's the x squared function, so -2 squared should not equal 2 squared. But then we get 4 is not equal to 4, and that's a contradiction because we know 4 is equal to 4. So therefore, we can say that this assumption is not a valid one. We can't assume that f is 1-to-1. That's how we prove that it is not 1-to-1. Anyway, I'd like you to start assignment 5A1, copy the problem list, and do the first problem, and I'll see you in class.